organizer for giving me this opportunity to present our research on the non-perturbative study of the isospin symmetry breaking. It's a theoretical study. Has been done in collaboration with my student at the time, Abdelmajid Diab, now is my colleague. My name is Abdel Nasser Tawfiq. I'm located in Cairo, Egypt. The agenda of my talk is as follows. First, I will start with a short review on the isobaric quantum spin. Then I will give a very, very short review on the non-perturbative QCD at finite isospin chemical potential in relation with finite isospin baryon chemical potential. Then I will focus on my talk on the QCD-like effective model. I mean the Polyakov linear sigma model, SU3. We use 3 flavors at finite isospin, as I said. After that, then I will present or show you some results on the thermodynamics we have generated from this model. And finally, I will come to the conclusions. More details about this talk is can be found in this paper. To explain the neutron-proton symmetry, Heisenberg, about 90 years ago, introduced the isobaric spin into nuclear physics. And Wegener added more details on that. Experimental confirmation of this quantum number was carried out in the 30s or 50s of the last century. Here you have some references. At that time, people have been thinking that the isospin asymmetry is applied on light nuclei only. But later on the 60s of the last century, Anderson et al. showed that the isospin is also important. It's important in heavy nuclei. What is this? The major difference between the nucleons in the sense that we have two members of this family, we have neutron and proton, are the charge. The neutron are uncharged while proton is charged. This binary nature of nucleon charge could be simply represented by some charge operator capital Q and its associated eigenstate chi of n, where you can have this operator Q affected on this chi of n, you get the eigenstates Q multiplied by the state. Q takes a value 0 and 1. This is a kind of binary system. For us now, the isospin is a vector quantity which can be also applied on quarks, on up and down quarks. For instance, for up and down quarks, the I vector quantity equals to 1/2, but both are distinguishable if we go to the third component, I3. I3 equals plus half for up and minus half for the down. And for all hadrons, regarding their up and down constituents here, we can apply this relation I3 equal 1/2 multiplied by nu minus nd, where finite I plays a major role in various physical systems. For instance, in the early universe, especially in this situation, we have very low or vanishing baryon chemical potential. What we can deal with in this case is the lepton, is a large lepton asymmetry. This could be also done. Also could play a role in a compact star where the pion condensation plays a very important role, and of course in the nuclear spectroscopy. Just a very short review what we know from the lattice QCD, non-perturbative lattice QCD at finite isospin. At finite isospin, the lattice QCD simulation has real and positive actions. Therefore, one can straightforwardly implement the Monte Carlo technique. I'm showing here 2 figures. One, the left one is from the non-perturbative QCD simulation. At finite isospin chemical potential, we have a kind of phase diagram here, and we show also where is the pion condensation are dominated. On the right hand side, we have here an called IR improved ADS QCD model. Even in this model, we can see a similar kind of phase diagram where we have here plotted, or people have here plotted the T versus the isospin chemical. What we think is that lattice QCD at finite isospin chemical potential and also at finite barium chemical potential share some common features. For example, the deconfinement or particle creation, silver place phenomena, which is related to that the system, your system, if you are at zero chemical potential, the thermodynamics are independent on the chemical potential up to some critical value. Then you have the dependency. Also, the common feature is in Bose-Einstein condensation. I move now to the Polyakov linear sigma model and try to estimate the impact of the isospin chemical potential in it. I will start with the Lagrangian density, which in this case consists of two parts: the chiral part and the Polyakov loop part. Chiral part in turn consists of two parts: one for the quarks, which are fermions, and the other part for mesons, which are bosons here. The second part, the Polyakov loop potential, is introduced to take into account the Golonic degrees of freedom and introduce dynamics to the quark-gluon interaction to our model. In our calculation, we utilize a kind of Polyakov loop potential, which counts for strong coupling and introduce higher orders of Polyakov variables. Phi are expressed in this form, where we have here generator Ta and sigma A and pi A. Sigma A and pi A are the scalar and pseudoscalar fields. In vacuum state U1, there is some anomaly, and as a result, as a result of the spontaneous symmetry breaking, the excitation value of mesonic and also of their conjugate are generated with some quantum numbers. This leads to exact vanishing mean value of pi A, but a sure finite mean value of sigma. And we can now assign sigmas to the different quarks. For instance, sigma 0 and sigma 3 and sigma 8. All of them are non-vanishing, and we can assign each of them to one type of the quarks. At the end, we have the expectation value of this phi, which is given in this T0 sigma 0 plus T3 sigma 3 plus T8 sigma 8, where the sigma 3 is a quantity, is the operator which breaks the isospin symmetry in SU3. Furthermore, the potential of the mosaic contribution in SUN can be given in this equation U of sigma, where the coefficient G and F are expressed in this very long expression. Now, if we try to determine the sigma, the different sigma 0, sigma 3, and sigma 8, we can start with a standard and anisotropic and symmetric structure of the theory. The symmetric structure constant DABC can be defined in this expression, where we can also use the BC-AC relation to relate these to the decay constants, which are related to the symmetric structure constant as follows. Say FA equals DAB sigma A. Accordingly, the decay constant of the charged and neutral pion mesons F pi plus minus equals F1 and F pi 0 equals F3. And for the K mesons, we have Fk plus and minus equal F4 and Fk0 equals F6. And they are given following: F pi 0 equals F pi plus minus everything equals the square root of 2/3 multiplied by sigma 0 plus 1 over sigma 3 multiplied by sigma 8, and the same can be also, you can see from for the sigma k plus k minus, and for fk0 as well, where the iso spin sigma field sigma 3, which is an important one, which we need to determine, is given as a difference between the decay constant of natural and charged cation in the form A. Sigma 3 equals the decay constant of sigma plus minus minus the decay constant of fk0. From the experimental and recent latest review on the physical constants, we have estimation for the decay constants, and accordingly have expressed that the H3, which is related to the sigma 3, yeah?
5 more minutes, please.
Yeah, okay. The H3 can be expressed in this very long expressions, where I can summarize it in the way that the square brackets is nothing but the squared mass of the A0 meson, and the sigma bar 3 is the difference between fk plus k minus minus f0. Therefore, we get the result that H3, which takes care for the isospin symmetry breaking, equals the mass square, the squared mass of Ma0 multiplied by the difference between fk plus minus minus fk0. As a result of the finite isospin symmetry, the masses of the quark flavors are as naturally preferred are not entirely degenerated. Therefore, we expect that the quark, the masses of up and down and mesos are distinguishable. They are not degenerate. To assure this situation, we use orthogonal basis transformation to convert the condensates sigmas to their original sigma 0, sigma 3, and sigma in this form, where we have now related sigma u's to sigma 0s and sigma d to sigma 3 and sigma s to sigma 8, for instance. Accordingly, the masses of the up, down, and s quarks can be expressed in this form here, where G is the Yukawa coupling. As mentioned, the potential of the pure mosaic contribution, we are now able to construct this from the equation 6, which I have shown before, and the potential term in the chiral linear sigma model Lagrangian density sigma can be constructed in this expression. For symmetry breaking in vacuum, we assume that capital H not equal to 0, and C is some constant not equal to 0 as well, and also lambda, and we assume also the masses of the different quarks are not degenerate. Using this table where we have our parameters, we can now generate the thermodynamics. To do this, we have to we can also relate the chemical potential to the different constituents, different quantum charge. For example, the baryon, the strangeness, electric charge, and the isospin, and these are elaborated in these three expressions. From our now we are able to construct our potential using the mean field approximation. We have here the sigma psi par psi, which counts for the three quarks and at finite temperature and finite chemical potential, where we are expressing here mu f, which counts for all the quantum charge, where in this expression also includes the Coulombic degrees of freedom. Done, we can now calculate the thermodynamics. Now here I'm comparing between the lattice calculation for the pressure normalized to T to the power 4 and our calculations. On the right-hand side, I'm giving here our expectations at finite isospin chemical potential. The same is done for the interaction rate on the bottom panel, where we are in good agreement with the lattice QCD, with the available lattice QCD, and we have as well our expectation at finite isospin potential. The same we have done for the higher moments for example, for these for moments of different quantum charge, for example, for the baryon, for chi-square, for baryon degrees of freedom, for charge degrees of freedom, and so on. We are comparing between lattice, and our agreement, I think, is convincing. And also we are giving our the same we have here elaborated for the susceptibility for different flavors, and we're comparing between the lattice, and we are giving expectation at finite isospin chemical. Now, here to summarize my talk, here is the phase diagram T versus mu I, where we are comparing between the available lattice. These are the dots, and these are this band, and our calculation are the solid line. To summarize or to conclude, we see that in SU3, the finite isospin symmetry makes the mean sigma fields having non-zero diagonal generators, sigma 0 and sigma 3 and sigma 8, and the parameter of explicitly symmetry breaking are non-vanishing as well. H0 not equal to H3, not equal to H8, all of them are finite. And we have estimated the H0, the parameter takes care for the isospin chemical, for isospin asymmetry. This means that the impact of the finite sigma 3 and H3 breaks SU3 isospin asymmetry, where we can determine sigma u for up quarks and sigma down and so on. To this end, we have we first driven the thermodynamic potential, pure mesonic contribution SU3 based in up-down and strange condensation, and with the Polyakov loop potential is integrated in our calculation to assure integrating Coulomb degrees of freedom in the chiral linear sigma model and the quark-gluon interaction. Thank you very much.
Okay, thanks for the hands up. We have maybe 1 minute for questions if anyone has any. We're already like 5 minutes off the schedule, so. Yeah, you have a question?
No, I have to be quick.
No, we'll go.
Okay, fine.
All right.
I'm good.
Yeah, thanks very much.
Thank you. Thank you very much. Bye-bye.